Alright, welcome back to Inorganic Tutors Institute, where we unlock minds with mathematics. Today's focus is going to be on product and quotient rules. I will explain them step by step and solve exam-style problems that you need to master. But before we continue, this video is proudly sponsored by WASSCE iPhones and laptops, your #1 plug for iPhones, MacBooks, JBL speakers, and many more. Visit WASSCE iPhones and laptops today at Circle Mall, Accra, and on UCC campus. Or you can reach out to WASSCE iPhones and laptops on +233 552 868 323. WASSCE iPhones and laptops, your #1 plug for iPhones and laptops. Okay, this topic shows up in every semester in both quizzes and in exams. Therefore, don't forget to master it to avoid losing easy marks in both quizzes and in exams. So, come close to the camera and let's start solving problems. Okay, so this is our first question, and we want to find the first derivative to this particular function, right? So, this here, we are going to use the quotient rule. Let me give you some clues before we begin. The quotient rule, what it does is that when you have two functions that are dividing, then you apply the quotient rule. And the product rule, what it also does is that when you have two functions that are multiplying, then you apply the product rule. Okay, so this is our first problem, right? So we want to find the derivative to this particular problem on the board. Okay, so this you have right here, we cannot differentiate it directly, right? So we have to apply the natural log to both sides. Okay, so step 1, introducing the ln, right, to both sides. We have ln y equals ln 10 to the power 1 minus x divided by 1 plus x, right? So this is what we have right now. Now, step 2. Recall that one of the properties of logarithm says that if you have log a to the power b or log a exponent b, then is equal to b log a, right? So this property is going to help us at this section. So we come down here, then we apply this property in here. So we're going to have 1 minus x divided by 1 plus x times ln 10, right? And this is a constant, right? So we keep it. Okay. Now we can see that we have two functions that are dividing, right? That is u equals 1 minus x and v equals 1 plus x. That is first function and second function, right? Okay. The quotient rule says that if you have two functions that are dividing, then first differentiate the first function, keep the second function, minus maintain the first function, differentiate the second function, all divided by the square of the second function. So, step 3, know the formula for quotient rule. So we have u divided by v equals u prime v minus u v prime divided by v all squared, right? So this is the rule for quotient. Okay, so all we need to do here is identify our u prime and our v prime, because we already have our u and we have our v. Okay, so our u prime here, from here we are going to have our u prime to be equal to derivative of 1 minus x with respect to x is going to give us minus 1. Derivative of 1 plus x with respect to x will give us positive 1, right? So this is what we have. Now, let's come up here. Ln y equals 1 minus x divided by 1 plus x ln 10. Okay, so we are going to apply the formula, okay? So u over v equals u prime v minus u v prime divided by v squared. Okay, so this is what we have at this point, and we have our u prime v, we have our u v prime. Okay, so what we need to do is to substitute, right? And don't forget, we are doing this to both sides. We are dealing this, we are working. Let's finish with the right hand side, then we come to the left hand side. Okay, so with the right hand side, we have identified our u prime, which is -1, and our v prime is +1. As well, our u and v is right here. So we're going to have ln y equals, our v prime is -1 and our v is 1 plus x, minus our u is 1 minus x, and our v prime is +1, divided by 1 plus x all squared. Okay, multiplied by ln 10, right? So we're going to have ln y equals -1 minus x minus 1 plus x, right? We expanded this bracket and we have -1. To this we have minus x. To that we have -1. To that we have positive x, all multiplied by ln 10, divided by 1 plus x all squared, right? So we can see that this cancels this, and then we are going to have ln y equals this, and this will give us -2. Then we have our ln 10, right? Divided by 1 plus x all squared, right? So this is what we have as it stands now. So we can see that this is equal to -2 ln 10 divided by 1 plus x all squared, right? Now, we are done with the right hand side. Let's come to the left hand side. Recall that if you have ln y, or if you have a function inside the natural log function, then what you have to do is that if you are interested in differentiating it, then step one, take 1 over the function inside the length, right? So you're going to have 1 over the function inside the length, which is y. So we have y here, times differential of the function inside the length. So we have y prime. Okay, so we can say that our ln y is equal to y prime divided by y. Okay, so that is the derivative of what? Ln y. So we are going to substitute this in here, right? We are going to substitute that. So when we come up here, then we can say that we have y prime divided by y equals -2 then 10 divided by 1 plus x all squared here. Okay, recall that y is equal to, from the question, y is equal to 10 to the power 1 minus x divided by 1 plus x, right? So here we can say that y prime divided by y times y should be equal to -2 ln 10 divided by 1 plus x all squared times y, right? Because we multiply here by y, we have to also multiply here by y. So this cancels this. Then we're going to have y prime to be equal to -2 ln 10 times y divided by 1 plus x all squared, right? And we said that our y is this, right? So we are going to substitute in place of this. So we're going to have y prime is equal to -2 ln 10 times y, which is this, which is 10 to the power 1 minus x divided by 1 plus x, or divided by 1 plus x all squared. Okay, so this becomes our final answer to the problem that was given, right? Very, very simple. So we have here -2 ln 10 times 10 to the power 1 minus x divided by 1 plus x all over 1 plus x all squared. Very, very, very simple. Okay, so now let's move on to the next problem. Okay, so with problem 2, we have two functions that are stacked together, right? So it means we have to apply the product rule, right? And the product rule says that if you have two functions that are stacked together, then first differentiate the first function, maintain the second function, plus maintain the first function, differentiate the second function. That is the product rule. Okay, so once you know this rule, then the rest is what? Differentiation. Okay, so we have to identify our u and identify our v. So our u here is our first function, right? So which is e to the power ax, and our v is cosec into bx plus c, right? So we have to also find our u prime. So our u prime here is going to be, we have an exponential function and you want to differentiate, that means you have to maintain the exponential function, then you differentiate the exponential function with respect to what? X. So you're going to have a differential of ax with respect to x, you're going to have what? A. Okay, then we find our v prime, right? So our v prime is going to be differential of cosec into bs plus c. Actually, if you want to differentiate cosec, then it's going to be what? Negative cosec cot x, right? So in here, we are going to have negative cosec into bx plus c times cot x cot into bs plus c, right? Then you differentiate the function inside the cosec, right? So we are going to differentiate this function what? With respect to x. And you know that if you differentiate bx plus c with respect to x, then you're going to have b, right? So you multiply all this function by b. right? So this is what we have for v prime, and this is what we have for u. So we just have to what? Substitute into the formula. Okay, so we're going to have y prime to be equal to our u prime is a e to the power ax, and our v is cosec into bs plus c, plus our u is e to the power ax, and our v prime is this, right? So we have negative cosec bs plus c cot into bs plus c times b, right? So this is what we have. Let's try to simplify that. When you simplify this, you're going to have a e to the power ax cosec into bx plus c plus, okay, so let's try to bring the negative out, right? So we have negative b e to the power ax multiplied by cxc negative b into csc into bx plus c cot into bx plus c right here. Okay, so this is what we have. So we can see that e to the power ax and cosec into bs plus c is common to these two terms, right? So we can factor that out. So when we do that, then we have y prime equals, we are factoring e to the power ax out, e to the power ax, and we are also factoring cosec into bs plus c out. So we have cosec into bs plus c out. So it means that what is left for the first term is only a. So we have a here. Then what is left for the second term is going to be minus b cot into bs plus c. So we have cot into bs plus c. Okay, so let's try to write it well. So we have y prime equals e to the ax cosec into bx plus c into a minus b cot into bs plus c. Okay, so this becomes our final answer to this particular problem. All right, it's very, very simple. You just have to apply the product rule very well. Note, if you have functions that are stuck together, don't try to differentiate them at once, right? Just try to identify your u, identify your v. Once you are done with that, differentiate your u, differentiate your v. Then you apply the formula. So you substitute them inside. And then we had this. Very simple, right? So let's move on to question number 3. So with problem number 3, we are going to apply the knowledge we obtained in problem number 1 and that of problem number 2. So with problem number 1, we use the quotient rule, right? And in problem number 2, we use the product rule. So we are going to use that here. Recall that the quotient rule says that when you have two functions, u and v, and they are dividing, then you're going to, and you want to differentiate, then you're going to differentiate the first term, which is u, then you maintain the second term, which is v, minus you maintain the first term, then you differentiate the second term, divided by square of the second term, right? That is the quotient rule. And this product rule also says that if you have two functions, u and v, and you want to differentiate, then differentiate the first term, maintain the second term, plus maintain the first term, differentiate the second term. So that is the product rule, and this is the quotient rule, right? So we can spot from this question number 3 that we have two functions that are stuck together at the numerator and two functions that are stuck together at the denominator. So here we are going to apply the quotient rule on both functions, but we apply the product rule on the numerator and we apply the product rule on the denominator as well. So our u will be equal to e to the 2x cos x, and our v will be equal to x sine x. Okay, so we have to identify our u prime and our v prime, right? So we come down here, our u prime will be equal to, we have two functions, right? So we differentiate the first function, which is e to the 2x, and we are going to have 2e to the 2x. Then we maintain the second function, which is cos x, plus we maintain the first function, which is e to the 2x. Then we differentiate the second function, which is cos x, and that is going to give us negative sine x. So we have negative sine x, right? So this is our u prime. Okay, now we differentiate the v for us to have our v prime. So our v prime will be equal to, we differentiate x, right? And we have 1. Then we maintain sine x, plus we maintain x, then we differentiate sine x, and that is cos x, right? So that is our v prime. Okay, so we have our u, we have our v, and we have our v prime, and have our u prime. Okay, so we can now substitute into the formula. So our y prime will be equal to, our u prime now is this here. So we have 2e to the 2x cos x minus e to the 2x sine x right here. So that is our u prime, right? Multiplied by the v, and our v is x sine x, minus our u, which is e to the 2x cos x, multiplied by v prime, which is sine x plus x cos x, right? Divided by v squared, right? And our v here is x sine x all squared, right? So you can see that if you first identify your u and your v and you differentiate them 1, 1, it's going to make the work very easy, right? So here we're going to have y prime equals, when you try to expand these brackets, that means we are going to have 2e to the 2x cos x sine x, right? Then we have minus x e to the 2x sine squared x, right? This and that. Divide minus, we spread this 2 here, we're going to have minus cos x sine x e to the 2x. Then this to that, we are going to have minus x e to the 2x cos x squared, cos squared x, right? Divided by x sine x all squared, right? So we can see clearly from here that this term and this term have something in common, right? So we're going to say that y prime equals this and this will go to one term. So we have 2x e to the 2x cos x sine x minus e to the 2x cos x sine x right here. Okay. Then this and this, they all have negative in front, right? So we bring negative out into x, negative out. This and this have e to the 2x common, right? So negative x e to the 2x out into sine squared x plus cos squared x, right? Divided by x sine x all squared, right? So this and this also have e to the 2x cos x sine x in common, right? So we bring that out, e to the 2x cos x sine x out, right? Into 2x minus 1, right? Minus x e to the 2x into sine squared x plus cos squared x, right? Divided by x sine x all squared. Okay, so this is what we have at this point. And recall that there is an identity that says that if you have sine squared x plus cos squared x, then you can say that they sum up to 1. So this is a property that is going to replace all this, right? So we're going to have y prime equals e to the 2x cos x sine x into 2x minus 1 minus x e to the 2x into 1, right? Divided by x sine x all squared. Okay, so we come up here, and then we have y prime equals e to the 2x cos x sine x into 2x minus 1 minus x e to the 2x divided by x squared sine squared x. Okay, so this becomes our final answer to this particular problem. Very, very, very easy. Follow the procedure and you are good to go. Now let's move on to the fourth problem, and let's look at it. So with question number 4, we want to differentiate this function inside the log, right? So first of all, we have to apply the log property, which says that if you have log A exponent B, then it's the same as B log A, right? So we are going to apply this property on this function. So we're going to have y equals 5 log into 3x squared plus 2, right? So this is what we have. Now we want to differentiate this. And before we can differentiate this, we have to change it to what? The natural log form, right? And we know that because this is of 3 base, then it's going to be in base 10. So we have 5 ln into 3x squared plus 2 divided by ln 10, right? So this is what we have. Now we want to differentiate this, right? And we know very well that differentiating a function inside the length function then means we are going to take 1 over the function inside the length function times the differential of the function inside the length function. So ln into 3x squared plus 2 will be equal to, derivative of that will be equal to 1 over 3x squared plus 2 times derivative of 3x squared plus 2 will be 6x, right? Now we're going to, let's say that we have 6x divided by 3x squared plus 2, right? So we are going to substitute this in place of that, right? So we are going to have y prime to be equal to 5 times 6x divided by 3x squared plus 2 times ln 10, right? So we're going to have y prime to be equal to this, and this will give us 30x divided by 3x squared plus 2 multiplied by ln 10, right? So this becomes our final answer to this particular problem. So whenever you have a function, right, inside this kind of log, then you have to change it to the natural log form before you can differentiate, right? So remember, if you have any function inside the natural log function and you want to differentiate, first take 1 over the function inside the length function times the differential of the function inside the length function, and that is it. Right, let's move on to question number 5. Okay, so with question number 5, we want to find the derivative to this particular function, right? So as usual, if you want to find derivative of a function inside the length function, then first take 1 over the function inside the length function, right? So we have y prime equals 1 over the function inside the length function. So we have sec x plus tan x times the derivative of the function inside the length function. And note, the derivative of sec x is basically sec x tan x, right? Sec and tan, they are stuck together. They are always moving hand in hand, right? So the derivative of sec x is sec x tan x. And the derivative of tan x is also sec squared x, right? So we have y prime to be equal to sec x tan x plus sec squared x divided by sec x plus tan x, right? So this is the derivative to this particular problem. Well, we can see that sec s. Okay, so we factor sec s out because sec s is common to these two terms and the numerator. So we have y prime to be equal to sec x out into tan x plus sec x, right? So we have this here divided by sec s plus tan x, right? So we can see that this takes off this, right? So we have y prime to be equal to sec x. So the derivative of this function is sec x. Okay, so let's move on with question number 6. We want to differentiate y equals e exponent square root of cot x, right? So first of all, let's change the square root into half, right? So we have y equals e exponent cot x exponent half, right? And so from here, we cannot differentiate this directly, right? We have to apply the natural log to both sides. So introducing the ln to both sides, we have ln y equals ln e exponent cot x exponent half, right? And one of the properties of logarithm says that if you have log a exponent b, then it is equal to b log a, right? So this is a property that we are going to apply on this. So we have ln y equals, we drop the exponent, right? We drop the whole of this, which is cot x exponent half ln e. Okay, so from here we know that ln e, but ln e is equal to 1. Okay, recall that. So now our function becomes ln y equals cot x exponent half, right? So now the work has become so easy for us to differentiate. Okay, so here we are going to apply the power rule, right? And the power rule says that if you have a function of this nature, right, and you want to differentiate, then you drop the exponent, right? Then you subtract 1 from the exponent, then you differentiate the function, right? So we're going to have ln y equals half times derivative of cot x is cot x times negative cosec squared x, right? Then we subtract 1 from half, and that is negative half. Okay, so that is the derivative to this particular function. So we bring the negative here, negative half cot x exponent half cosec squared x. So you have ln y here, right? And remember that derivative of ln y is equal to y prime over y, right? So this is what we are going to use here. So we have y prime divided by y equals negative half cot x exponent negative half cosec squared x, right? So we have y prime divided by y equals negative half cot x exponent negative half cosec squared x, right? And we know that cot x exponent negative half is the same as 1 over square root of cot x, right? So we change this to that in here. So we're going to have y prime divided by y equals negative half times 1 over square root of cot x times cosec squared x, right? So we bring this up. So we're going to have negative cosec squared x divided by 2 times square root of cot x, right? So this is what we have at this point. And remember that y was giving us this. So we have e to the power square root of cot x, right? So we substitute this here. Okay, so we're going to have y prime divided by y times y equals negative cosec squared x divided by 2 square root of cot x times y. Because we multiplied here by y, we have to also multiply here by y. So this takes off this. Then we have y prime equals negative cosec squared x divided by 2 square root of cot x times y, right? So we are going to have y prime equals negative cosec squared x y divided by 2 square root of cot x, right? So we substitute our y, of which is equal to e to the power square root of cot x divided by 2 square root of cot x, right? So this becomes the result of differentiating this particular function. So we see that the derivative of e to the power cot x, e to the power square root of cot x is negative cosec squared x times e to the power square root of cot x divided by 2 square root of cot x, right? Okay, so that is the derivative to this particular problem. Now let's move on to question number 7. Okay, so with question number 7, we want to find the derivative of cos x ln x e to the x squared x to the x, right? So we can see that we have 1, 2, 3, 4 functions, right? And we have to differentiate them. Okay, so in here we are going to apply the natural log properties and the properties of logarithm, right? So we have to first introduce ln to both sides, the natural log. So step 1, introduce ln to both sides, right? So we have ln y equals ln into cos x ln x e to the x squared x to the x, right? So this is what we have. Now at this point, we have to apply the natural log property, right? That says that if you have log AB, right? If you have log AB and you want to separate them, then it's going to be what? Log A plus log B. That is a property of logarithm. So we know this. Okay, so we are going to apply it on this. So we have log y equals ln. Let's try to spread the ln across board before we separate them. So we have ln cos x times ln into ln x times ln into e to the x squared times ln x to the x, right? So from here, we are going to apply this. So we're going to have ln y equals ln cos x plus, because it is multiplying, we add, right? So we have ln into ln x plus ln e to the x squared plus ln x to the x, right? So this is what we have. Now, for us to be able to differentiate it with ease, we have to differentiate it one after the other, right? So we pick the first term, differentiate, pick the second term, differentiate, pick the third term, differentiate, then we pick the last term and also differentiate, then we combine all, right? So let's start from the left hand side. So ln y, derivative of ln y with respect to y is going to be 1 over y times derivative of y, right? We take 1 over the function inside the ln, then we differentiate the function inside the ln, right? So derivative of ln y is equal to y prime divided by y. So that is what we have for the left hand side. So we come to the right hand side and pick it one after the other. So we're going to start with ln cos x, right? So we differentiate ln cos x, and we're going to have, we're applying the same properties. We take 1 over the function inside the ln times derivative of cos x, and that is negative sine x. So we have negative sine x over cos x. Now recall that tan x is equal to sine x over cos x, right? So we are going to substitute tan x in place of this. So we're going to have negative tan x. So that means that the derivative of ln cos x with respect to s is equal to negative tan x. So that is the first term. We are done with that. We come to the second term, which is ln into ln x, right? So derivative of ln into ln x with respect to x will be equal to, we take 1 over the function inside the ln, which is 1 over ln x, times derivative of ln x. So that's going to be 1 over what? X, times derivative of the function inside the ln, which is x, and that is going to be what? 1. So we have in all derivative of ln into ln x with respect to s to be equal to 1 over x ln x, right? So we have the second term on the right hand side differentiated. So we move to the third part, which is derivative of ln into e to the x squared, right? So in here, we have to drop the x squared before we can differentiate. So x squared ln e. And remember that ln e is equal to 1. So we're going to have derivative of x squared to be equal to 2x, right? So this implies that derivative of ln into e to the x squared is equal to 2x, right? So we have first term, second term, third term. Left with the last term, which is ln into x to the x. So derivative of ln into x to the x is equal to, we have to drop this x, so we have derivative of x ln x, right? And this we are going to apply the product rule, okay? So here, our u is equal to x, v is ln x. So v prime will be 1, and u prime will be 1, and v prime will be 1 over x, right? So if you apply the product rule, we are going to have 1, then our v is ln x, plus our u is x, and our v prime is 1 over x, right? So in all, we have ln x plus this cancels this, we have 1 here. So that means that the derivative of ln into x to the x is equal to ln x plus 1 here. So beautiful, right? So we have the first term, second term, third term, and the fourth term differentiated. So we are going to combine all. Okay, so let's come up here. Okay, so let's combine all. We're going to have y prime divided by y equals, first term is negative tan x, and the second term is 1 over x ln x, and the third term is plus 2x, and the fourth term is ln x plus 1, right? So that is what we have for derivative of this. Now, we know that we have to take this away, the y. So we multiply here by y, multiply here by y. So this takes off this. We have y prime equals negative tan x plus 1 over x ln x plus 2x plus ln x plus 1, all multiplied by y. But remember that from the beginning, we said that the y should be equal to this. That is the question. So we're going to substitute that here. So we have y prime to be equal to negative tan x plus 1 over x ln x plus 2x plus ln x plus 1, all multiplied by y, which is cos x ln x e to the x squared x to the x, right? So let me write that gently here. So we have y prime equals negative tan x plus 1 over x ln x plus 2x plus ln x plus 1, all times cos x ln x e to the x squared x to the x. Okay, so this becomes the derivative to this particular problem. Very, very simple, right? So whenever you have a problem, right, derivative, a function that you want to differentiate, don't take it in bulk, right? Take it one after the other, and the work will be very easy for you. So the derivative of this particular function is what we have right here. Now let's move on to question number 8. Okay. So with question number 8, we want to differentiate ln into a plus b tan x divided by a minus b tan x, right? So first of all, we have to remember that if you want to differentiate any function inside the ln, you take 1 over the function inside the ln times derivative of the function inside the ln, right? So in here, we are going to take 1 over the whole of this function. Then we differentiate this right here, okay? And you know that before we can differentiate this, we have to use the quotient rule because we have two functions dividing each other, okay? Okay, so let's proceed. So first of all, we have y prime to be equal to 1 over the function inside the ln. So we have 1 a plus b tan x divided by a minus b tan x, right? Times derivative of the function inside the length, and that is a plus b tan x divided by a minus b tan x, right? So this is what we have. Now, for us to differentiate this, we know we are going to apply the quotient rule. So let's handle this, right? So that is going to be derivative of a plus b tan x divided by a minus b tan x, right? So quotient rule says that you differentiate the first function, maintain the second function, minus maintain the first function, differentiate the second function, divided by square of the second function. So we identify our first function here to be u, and that is a plus b tan x, and our second function is a minus b tan x, right? So that is what we have to do first. Now we have to find our u prime, we have to find our v prime. So from prime, and we need v prime. So our u prime will be equal to derivative of a, which is a constant, will be 0. Then we differentiate b tan x, and that is going to be, b tan x, we have to apply the product rule. But b is a constant, so when we differentiate it, it will be 0. And 0 multiplied by tan x will give us 0. So we maintain b, then differentiate tan x. Derivative of tan x is sec squared x, right? Then we come to our v prime, which will be equal to, we differentiate a, which is a constant, and that goes to 0. Then we differentiate b, and that is also constant, and that goes to 0. So 0 multiplied by tan x is 0. So we maintain, now we maintain the b, the minus b, then we differentiate tan x, and that is sec squared x, right? So we have u prime, we have v prime, and as usual, we have u and we have v, right? So we are going to insert into the formula, then we have the derivative of that to be equal to u prime is b sec squared x, and our v is a minus b tan x, minus our u is a plus b tan x, and our v prime is negative b sec squared x, right? Divided by v squared. So we're going to have negative b a minus b tan x all squared, right? So we are going to have that to be equal to b a minus b tan x times b sec squared x minus into minus b sec squared x into a plus b tan x, right? Divided by a minus b tan x all squared, right? So this, we can expand that, and we have a b sec squared x minus b squared tan x sec squared x, right? Then this and this will be positive, so plus b ab sec squared x plus b squared tan x sec squared x, right? Divided by a minus b tan x all squared, right? And from here, you can see that this is positive, this is negative. So this automatically takes off this. And then this and this becomes 2ab sec squared x divided by a minus b tan x all squared. Right. So that is the derivative of a plus b tan x divided by a minus b tan x. So that is what we have for this. So we're going to substitute this here. So we're going to have y prime to be equal to 1 over a plus b tan x divided by a minus b tan x times 2ab sec squared x divided by a minus b tan x all squared, right? So in here, we know that if you have a over b over c, then you're going to have a times c over b. So you are going to apply that same knowledge here to have y prime to be equal to a minus b tan x divided by a plus b tan x, right? So times 2ab sec squared x divided by a minus b tan x all squared, right? So this is what we have. Now, this is a minus b tan x, and this is a minus b tan x all squared. So it means this can take one of this. So we're going to have our derivative to be equal to, this will take one of this, leaving a minus b tan x, right? So we have 2 sec squared x divided by a plus b tan x times a minus b tan x, right? So basically we're going to have this to be equal to 2 sec squared x divided by, this is difference of two squares, right? So we can say that we have a minus b tan x or squared. Or we can say that this is the same as 2 sec squared x divided by a squared minus b tan x or squared, right? This is the same as this, okay? This is the same as that. So that is the solution to question number 8. Now let's move on to question number 9. Question number 9, we want to differentiate this particular function, tan x to the power cot x plus sec x to the power x, right? So in here, we have first term, second term, okay? So if you want to differentiate this, very advisable to separate them term by term and differentiate. Once you are done, you combine them. Okay, so let's say that this term, we are considering this term to be a. So a equals tan x to the power cot x, right? And before we can differentiate this, we have to introduce the natural log to both sides. So we introduce the natural log to both sides, and we have ln tan x to the power cot x, right? And one of the properties says that if you have log a b, log a exponent b, then you have b log a. So this property is going to help us at this point. So we have ln a to be equal to cot x ln into tan x, right? So this is what we have right now. And this, we have to apply the product rule on the right hand side. Then we can use the properties of the differentiating ln functions at this point. So Let's do this first, then we come to this. So derivative of ln A with respect to A will be equal to A prime over A, right? So we have this done. Let's come to this. Derivative of cot x ln into tan x, right? And this, we are going to use the product rule. And the product rule says that when you have two functions stacked together, then you differentiate the first function, maintain the second function, plus maintain the first function, differentiate the second function, right? And our first function here is u, which is cot x, and our second function is ln into tan x, right? So we have u, we have v. So we come up here and we say that u prime will be equal to derivative of cot x is negative cosec squared x, right? And the derivative of ln into tan x, as usual, you take 1 over the function inside the ln times derivative of tan x. And derivative of tan x is sec squared x. So we have sec squared x, right? So we say that our v prime is equal to sec squared x divided by tan x. Okay, so we are going to use the rule that we stated. Okay, that is u prime v plus u v prime. Okay, and our u prime is negative cosec squared x, and our v is ln tan x, plus our u is cot x, and our v prime is sec squared x over tan x. So we can say that in all, we have cot x sec squared x divided by tan x minus cosec squared x ln into tan x. Right, so that is for the right hand side. And the left hand side, so we had this. So in all, we have a prime divided by a equals cot x sec squared x divided by tan x minus cosec squared x ln into tan x. Then we multiply here by a, multiply here by a, and this cancels this, right? But from the beginning, we said that a should be equal to this. So we are going to have the first derivative, the first term, to be equal to derivative of tan x to the power cot x to be equal to cot x sec squared x divided by tan x minus cosec squared x ln into tan x, right? All multiplied by the a, which is ln into tan x to the power cot x, right? So we have the first part done. So we come to the second part, right? So we come to the second part. We say that let b equals sec x to the x, right? So in here as well, we're going to introduce the natural log. So we say that ln b should be equal to ln into sec s to the x, right? So we use the properties that says that log AB is equal to A, right? So we're going to have log ln B to be equal to x drops down. We have ln into sec x, right? Now we know that the left hand side derivative of ln B with respect to B is B prime over what? B, right? So we have the derivative of the left hand side. We come to the right hand side, we apply the product rule because we have two functions stacked together. So x ln into sec x, derivative of that with respect to x, right? So our u here is equal to x, and our v is ln into sec x, right? And we know that we have to find our u prime, we have to find our v prime. So our u prime is equal to 1, and our v prime is equal to, we know that derivative of sec x is sec x tan x, right? So we have sec x tan x, right? So we have our v prime to be equal to sec x tan x divided by sec x, right? So that is the derivative of v prime. But we know that this can take off this, so v prime now becomes tan x. Okay, so let's come up here and combine them, right? So we can say that b prime over b will be equal to u prime v plus u v prime, right? And our u prime is 1, and our v is ln into sec x plus our u is x, and our v prime is tan x. So we have tan x. So in all, we have b prime over b to be equal to ln into sec x plus x tan x, right? And this, we know that the b will multiply here, right? So you have this taken of this, and then we have b prime to be equal to ln sec x plus x ln x tan x, all multiplied by b. But from the beginning, we said that b should be equal to sec x to the power x. So we say that we have b prime to be equal to ln sec x plus x tan x multiplied by b, which is sec x to the power x. So that is the derivative of the second term. So we're going to add this to this. Then the result becomes our derivative of the whole function, right? So with question number 10, we want to determine the value of dy dx when x equals 4, given that x squared plus y squared equals 25. All right, so this particular question, we have to determine dy dx when x is 4, given this function, right? So first of all, we know that x squared plus y squared has been given, right? So we have to substitute when x is 4 to find the value of what? Y. So y squared equals 25 minus x squared, right? And x is 4. So we have y squared equals 25 minus 4 squared, right? So we have y squared equals 25 minus 16. right? So we have y squared equals 9. Okay, so it means that y is equal to plus or minus 3. Okay, so once we have the value of y, then we can go ahead and differentiate this particular function with respect to x. So d with respect to x of x squared plus y squared equals 25, right? And it means that we are differentiating each of the term with respect to x. So we have x squared plus y squared equals 25, right? So this we are going to have 2x dx over x plus 2y dy over the x equals 0. Derivative of a constant is 0. Now, this takes off this, and then we have 2x plus 2y dy over the x equals 0. So, making dy dx the subject, then we are going to have dy dx to be equal to negative 2x over 2y. Now, we have the value of x to be 4, and we have the value of y to be plus or minus 3. So it means that we are going to substitute value of x and the value of y to find the values of dy dx. So when x equals 4 and when y equals positive 3, we're going to have dy dx to be equal to negative 2 into 4 divided by 2 into what? 3. So we have minus 8 divided by 6. So this 2 goes here 3, 2 goes here 4. So we have minus 4 over 3. So the first value is negative 4 over 3. Now we are going to consider when x equals 4 and y equals negative 3, right? So we are going to substitute here. Then we have dy dx equals negative 2 into 4 over 2 into negative 3. So we have dy dx to be equal to negative 8 over negative 6. So we have this cancels this, and this cancels this, 4, 3, and then we have 4 over 3. So it means that we have positive 4 over 3 and negative 4 over 3 as the values of x dy dx. So let me write it here boldly for you. So we can say that hence the values of dy dx are negative 4 over 3 and positive 4 over 3. Or we can equally say that dy dx is equal to plus or minus 4 over 3. So if you go to your quiz room and you are to determine the values of dy dx when x value is given and you are given a particular function, right? That means that you have to look for the value of y as well, so that after differentiating, you substitute the value of x inside, substitute the value of y inside. Then you find the first value of what? Dy dx. Then you substitute the other, then you find the other value of dy dx. It's very simple. You just have to follow the principle and you're good to go. Now let's move on to question number 11. Right. So with question number 11, we want to prove that x dy dx is equal to y squared over 1 minus y ln x, right? So first of all, we have been given this function, right? So it's either we use this to prove this or we use this to prove that. But the best way to go is to use this to prove that, because it is easy to use this to prove this. Okay, so let's begin. So if we observe y equals x to the x up to infinity, we can see that we can represent this right here by, we can let y equals x to the x to infinity, right? So if y is representing the whole of this, then it means that we can say that y is equal to x to the y, right? So we have this right here. So before we can solve this, from the beginning of the lesson, we learned that if you have any non-exponential function, then you have to introduce ln to both sides, right? So introducing ln to both sides, we have ln y equals ln x to the y, right? So from here, we use the log properties. The log property says that log a to the b is equal to b log a, right? So we're going to use this property to drop this y. So you have ln y is equal to y ln x. Very interesting. So from here, we are going to differentiate this side, then differentiate this side. So on the right hand side, okay, let's begin with this. So derivative of ln y with respect to y, we are going to have, we take 1 over y times derivative of y. So we have the right hand side done. So we consider this, right? So we know that y ln x, we have to apply the product rule to be able to differentiate this, right? So we let u equals y, v equals ln x, right? So in here, if you want to differentiate, it means that since we are using the product rule, then we know that this is equal to u prime v plus u v prime, right? So we need u prime, which will be equal to derivative of y, which is going to be dy dx, right? Then we need v prime. Derivative of ln x is 1 over x times derivative of x, which is 1, right? So basically, v prime is 1 over x. Okay, so we have u, we have v, we have u prime, and we have v prime. So what we need to do is to substitute into the formula. Okay, so we can see that the derivative of y ln x will be equal to u prime is dy dx, and v is ln x. So we have times ln x plus our u is y, and our v prime is 1 over x, right? So we can have ln x dy dx plus y over x. So this becomes the derivative to the right hand side. Okay, so it means that we are going to put this here, then we put this there. So we're going to have y prime over y is equal to ln x dy dx plus y over x, right? So this we have here, we know very well that this, we can throw this y here so that we have this times y, this times y, right? So this cancels this, and we have y prime to be equal to ln x dy dx plus y over x multiplied by y, right? We can spread this y throughout the brackets to have y ln x dy dx plus y squared over x, right? So from here, since we want to prove that this we have here, since we want to use this to prove this, then we have to make sure that we arrange this to resemble this, right? So we have to make dy dx the subject, but we don't need this x to be here, okay? So we come up here, then we say that y prime is equal to y ln x dy dx plus y squared over x, right? So we know that this over here, we can send this here, right? So that we have, okay, so we know that this here is y prime is the same as dy dx, right? So we have dy dx, then we send this here, we have minus y ln x dy dx equals y squared over x, right? So we factor y dy dx out, and then we have dy dx into 1 minus y ln x equals y squared over x, right? So we need to make dy dx the subject, but there is this fraction that we can try to avoid it here, so that we can have dy dx into 1 minus y ln x equals y squared over x. So when we multiply through by x, we have here x, we have here x. So this cancels this, and then we have x dy dx into 1 minus y ln x equals y squared, right? So now we are interested in the dy dx, right? So let's divide here by 1 minus y ln x, here by 1 minus y ln x. So this takes off this, and then we have x dy dx equals y squared over 1 minus y ln x. Okay, so this becomes our proof. So clearly we can say that our x dy dx is equal to y squared divided by 1 minus y ln x. Right? Hence, proven as record. Very beautiful, right? So you have to just follow the procedures and you are good to go. So you see, we made sure that we make x to the infinity represent what? Y. So since this whole of this that we don't know the end represent y, then you can say that x to the y equals y. So since we have been able to say that y is equal to x to the y, then you can easily differentiate this using the properties of logarithm. And you're good to go. And that is what has helped us to prove this. That is very simple, right? So let's move on to question number 12. So with question number 12, we have been given this function, right? And we want to prove that dy dx is equal to y squared cos x over 1 minus y ln into sine x, right? So we are using this to prove this, as we did in question 12, as we did in question number 11. Okay, so here we are going to also say that let y equals this function that we don't know where it is going, right? So x sine x to the x. Okay, so the whole of this is now y, as you see here. So we can say that y is equal to sine x to the y, right? So before we can differentiate this, we have to apply the natural log properties. So we know that log a exponent b is equal to b log a, right? So we can see that we have y equals y sine x. So here we have to introduce ln or ln to both sides. Then we have ln y equals y ln into sine x, right? So this is what we have. Now we are going to differentiate this, and this we are going to use the product rule because we have one function, we have the second function, right? So let's deal with this first. So derivative of ln y with respect to y will be equal to 1 over y times y prime. So that means that we are done with the left hand side. We have to take this y ln into sine x, right? So this means that our u will be equal to y and our v is ln into sine x, right? So this means that if you need u prime, we have dy over the x. Then our v prime will be equal to derivative of ln into sine x will be equal to 1 over sine x times derivative of sine x is cos x. So it means that our v prime will be equal to cos x over sine x. And recall that cos x over sine x is equal to cot x, right? So it means that our v prime is cot x. Okay, so once we have v prime, u prime, v, and u, then we apply the formula. So we know that uv is equal to u prime v plus u v prime. Okay, so right from here, you're just going to substitute. So our u prime is dy dx. So we have dy dx times our v is ln sine x plus our u is y and our v prime is cot x. Okay, so let's try to arrange it all. So we have ln sine x dy dx plus y cot x. Okay, so that becomes the derivative to the right hand side, right? So we combine the left and the right to have ln sine x dy dx plus y cot x. Okay, so we have to avoid this here. So we multiply here by y, multiply here by y. So this takes off this, and we have y prime to be equal to let's spread the y throughout the brackets. So we're going to have y ln sine x dy dx plus y squared cot x right here. So this is what we have at the moment. Now, we want to make sure that we express this term to have this. So we need to make dy dx the subject. And remember that y prime is the same as dy dx. Okay. Okay, so we're going to substitute that to have dy dx equals y ln sine s dy dx plus y squared cot x. Okay, so now we bring this here and then remain this here. So we have dy dx minus y ln into sine x dy dx equals y squared cot x. So we factor y dy dx out. So we have dy dx into 1 minus y ln into sine x equals y squared cot x. Okay, we need dy dx, so we divide through by this. So we're going to have this 1 minus ln sine x 1 minus y ln sine x, right? So this takes of this, and then we have dy dx to be equal to y squared cot x divided by 1 minus y ln sine x. Okay, so this has helped us to prove what we want. So therefore, hence proving as required. Very easy, right? Now, let's move on to question number 13. With question number 13, we want to show that this is equal to this, right? And we have been given this, okay? So, as we did in question 11, 12, we are going to apply the same knowledge in here. So, over here, let's say that y should be equal to the square root of ln x plus square root of ln x plus to infinity, right? So the whole of this has been represented by y. So we say that y is equal to square root of ln x plus this is y. So we have y. Okay, so we have simplified the expression to the lowest term so that we can differentiate. Now, before we can differentiate this, we have to square both sides, right? We have to square both sides before we can differentiate. So, squaring both sides, we have y squared is equal to ln s plus y, square root of that all squared. So this cancels this, and then we have y squared equals ln x plus y. Very easy, right? So now we can go ahead and differentiate both sides. Okay, so with this that we have here, it means we have to differentiate this, then we differentiate this, right? And for us to differentiate this, we don't need to apply the product rule at this point, right? So we differentiate this here, we're going to have, with respect to y, of y squared, we're going to have differential of this plus y with respect to x, right? So when you differentiate y squared with respect to x, we're going to have 2y dy dx equals differentiate ln x plus differentiate y. Okay, so we're going to have 2y dy dx equals derivative of ln x will be giving us 1 on x times 1 plus dy dx. Okay, so we are done with the derivation. So we have to group like terms to find our dy dx. So we go up here, then we have 2y dy dx equals 1 on x plus dy dx, right? So we bring this here, then we remain this. So we have 2y dy dx minus dy dx equals 1 on x, right? So we factor dy dx out, then we have 2y minus 1 equals 1 on x. Okay, so now we are interested in dy dx. So what we do, we can divide through by 2y minus 1, right? So we are going to have 2y minus 1 here, 2y minus 1. So this takes off this, and we have dy dx equals, when you have a over b over c, then it's the same as a over b times b over 1, right? So we are going to apply the same knowledge here, 1 over x times 2y minus 1 times 1 over 2y minus 1, right? So we are going to have dy dx equals 1 over x into 2y minus 1. And that proves our problem. Very interesting, right? You see the way the proofs keeps making the lesson interesting is because we have understood the product and the quotient rule very well, and how to differentiate the lane functions. So trust me, if you master these things very well, differentiation will become very, very cheap too. So here we can conclude that this is our conclusion, hence proven as record. Very, very easy, right? So now let's move on to question number 14. So with question number 14, if this x to the y is equal to exponential function to the x minus y, we want to prove that dy dx is equal to ln x over 1 plus ln x all squared, right? So we are going to use this to prove this. So we say x to the y equals e to the x minus y. So here we have to introduce the natural log to both sides. So when we do that, then we have ln x to the y equals ln e to the x minus y, right? So this drops down and this also drops down. So we have y ln x equals x minus y ln e. But we know that ln e is 1. Okay, so it means that we are going to have y ln x equals x minus 1, since this is 1. Okay, so this is what we have now. And we want to differentiate it so that we can have this that we have right here. Okay, so now let's group like terms. Okay, let's group like terms and put all y to one side and put all x to one side. So here we are going to have y ln x plus y equals x. So when we factor y out, we have y into ln x plus 1 equals x. Divide here by ln x plus 1. Divide here ln x plus 1. So this takes off this. Then we have y equals x over ln x plus 1. Okay, so before we can differentiate this, then it means that we have to use the quotient rule. We have to use the quotient rule. So from the beginning, we learn the quotient rule, we learn the product rule as well. So if you want to use the quotient rule, then we come here, x over ln x plus 1, right? So the quotient rule says that if you have two functions that are dividing, then differentiate the first function, keep the second function, minus keep the first function, differentiate the second function, all divided by square of the second function. So here, our first function is what? X, and our second function is ln x plus 1. So derivative of x will give us 1, and derivative of ln x will give us 1 over x, right? So 1 over x times 1 plus 0. So it means that our derivative of v is 1 over x, and that of u is 1. So we just have to apply the formula, which is u on v equals u prime v minus u v prime divided by v squared, right? So we are going to substitute them, then we simplify. So we're going to have u prime, which is 1, and v is ln x plus 1. Ln x plus 1 minus u is x, and our v prime is 1 over x divided by v squared, and v is ln x plus 1 all squared. So we have ln x plus 1 minus this cancels this, so we have 1 divided by ln x plus 1 all squared. So it means that this positive 1 will take off this negative 1. So we have ln x divided by ln x plus 1 all squared. Okay, so we have been able to differentiate the right hand side, and the left hand side is just dy dx. So we are going to have our final work to be dy dx equals ln x divided by ln x plus 1 all squared. Or we can rewrite this as dy dx equals ln x divided by 1 plus ln x all squared. And that proves our problem. Very, very easy, right? So I told you, you have to master the product and the quotient rule, and everything in differentiation is going to be very easy for you. Now let's move on to question number 15. So with question number 15, we want the second derivative of cos into ln x, right? So we are going to apply the chain rule before we can proceed, right? You know, the chain rule is applicable when you have a function embedded in another function, right? Like we have here, cos has taken ln onto itself, right? Ln is embedded in cos, so we have to apply the chain rule. So we have y prime equals, when you differentiate cos, is negative sign. Then we put whatever is inside times, we differentiate the whatever is inside. I know that derivative of ln x is 1 over x times derivative of what the function inside the ln is 1. So we have y prime to be equal to negative sine into ln x divided by x. Okay, so this is what we have at this point. Now, we want the second derivative of this. Okay, so second derivative. So with the second derivative, we are going to apply the quotient rule because we have two functions that are dividing each other. Okay, so we have to identify our u. So our u here will be negative sine into ln x, and our v will be x. So u prime will be equal to, we are going to apply the chain rule again. So we differentiate sine. Differential of sine is cos. So we're going to have negative cos into ln x times, we differentiate the function inside the ln, right? And that is the function inside the sine, and that is 1 over x. So we have 1 over x times 1, right? So our u prime will be negative cos into ln x divided by x. So that is the derivative of the u. So u prime is what? Negative cos into ln x divided by x. So we have to find v prime as well. Derivative of x is 1. So we have to apply our formula u over v equals u prime v minus u v prime divided by v squared. All right, and we know our u prime to be negative cos into ln x divided by x times our v is also x. So we have times x minus our u is negative sine into, so negative negative is going to be plus. So we have plus sine into ln x, and our v prime is 1. So we have 1 divided by v squared, and v here is x. So we have x squared, right? This basically cancels this. So we have negative cos into ln x plus sine into ln x divided by x squared. Okay, so this is what we have for the second derivative. So we can reposition this to have sine into ln x minus cos into ln x divided by x squared. Okay, so that becomes our second derivative to this particular problem, right? So that is our second derivative is, our second derivative is okay. So that is the second derivative to this particular problem. Very, very easy, right? So once you understand the quotient rule, the product rule, everything becomes very easy for you. Now let's move on to question number 16. So with question number 16, we want to find the second derivative to this particular function, y equals x to the x. So first of all, we have to apply the natural log function, right? So introducing the ln to both sides, we have ln y equals ln exponent x, ln x exponent x. So this will give us x ln x, right? So once we are at this stage, the rest is what? Very easy, because you know we are going to apply the product rule because we have two functions that are stacked together. Good. So let's deal with this first. We're going to have y prime divided by y. So the derivative of the left hand side is this. Let's consider this. X ln x. We are going to apply the product rule. So our u will be equal to x and our v is ln x. Okay, so it means that our u prime will be 1 and our v prime will be derivative of ln x is 1 over x. Okay, so we have all that we need. So it means that we're going to have uv equals u prime v plus uv prime, right? And our u prime is 1, right? So we have 1 and our v is ln x plus our u is x and our v prime is 1 over x. So we have ln x plus this cancels this, so we have 1. So the right hand side, this is the result that we have. So in all, we have y prime over y equals ln x plus 1, right? So we move this here, so we multiply here by y, here by y. So we have y prime equals ln x plus 1 or y. Now, don't forget that y is what? X to the x from the question. So we can say that our first derivative is x to the x. So we either use this or this. All are correct. So this is our first derivative. So we want the second derivative. So it's up to you. It's either use this to solve the second derivative or use this to solve the second derivative. For me, I'm going to use this to solve the second derivative. Okay, so for the second derivative, we're going to have y prime prime equals derivative of ln x plus 1 multiplied by y. So we are going to pick this to differentiate, okay? So we consider ln x plus 1 multiplied by y, and this is equal to y ln x plus y. So this means that we are going to use the product rule, then we apply normal differentiation on this. Okay, so y ln x plus y, we want to differentiate this, right? So we apply the product rule on the first term. Then when we are done, we differentiate this. The derivative of y is dy dx, right? So we consider this. So our u is y and our v is ln x. So u prime will be dy dx and v prime will be 1 over x. So u prime v plus u v prime will be equal to our u prime is dy dx plus, and our v is ln x plus our u is y and our v prime is 1 over x. Okay, so we're going to have ln x dy dx plus y over x. So this is what we have for the first term. And we know that derivative of y with respect to x is dy over the x. Okay, so we combine this and this, then we know our final solution. So we are going to have ln x dy dx plus y over x plus dy over the x this is the right hand side, and we know that the left hand side is y prime prime, and that is equal to this ln x dy dx plus y on x plus dy on the x, right? So let's group terms, this to this, and then we keep this there. So we're going to have y prime prime equals dy over dx into ln x plus 1 plus y over the x, y over x, right? So now we know that this is y prime, okay? So y prime prime is equal to, recall that dy dx is equal to y prime. And okay, and we had the y prime, which is the first derivative, to be x to the x into ln x plus 1. Okay, so this is what we had for the first derivative, right? So we are going to substitute this here, or y prime was y into ln x plus 1. So this and this, they are all the same. So either substitute this here or substitute this here. So our second derivative will be equal to y prime multiplied by ln x plus 1 plus y over x. Okay, so we are going to have our second derivative to be equal to y into ln x plus 1 plus y prime into ln x plus 1 plus y over x, or y prime prime equals x to the x, x to the x, since y prime is equal to this and is equal to dy dx, then it means we can substitute this here, right? And then either substitute this also here. So we're going to have our second derivative to be equal to x to the x into ln x plus 1 times ln x plus 1 plus y over x. Okay, so this is what we have. Now, this can be expressed as, okay, so we have this here, and don't forget y2 is here, so it means that we can substitute this over here. So we have our second derivative to be x to the x into ln x plus 1 ln x plus 1 plus x to the x over x, x to the x, right, over x. Now we can see that x to the x is common to these two terms, so we say that our second derivative will be x to the x out. Then we have ln x plus 1 ln x plus 1 plus 1 over x. Okay, so this becomes our final solution to this particular problem. That is our second derivative to this particular problem. Very, very easy, right? So for this to be easy for you, you have to master the quotient and product rule. For differentiation to be very cheap for you, you have to master those things, right? Now let's move on to question number 17. With question number 17, we want to find the second derivative of y equals a to the x times a times x to the a, right? So we can see that it's two functions multiplied, right? So we have to use the product rule. But before we can use the product rule, we have to apply the natural log function, right? So introducing len to both sides, so we have len y equals len into ax, x to the a. So you have len y equals, you know that one of the properties of logarithm says that if you have log ab, then it's the same as log a plus log b, right? So we are going to apply this on this. So we have len y equals len a to the x plus len x to the a, right? So in here as well, we're going to say that log a to the b is equal to b log a, right? So we apply this property on this. So we're going to have len y equals x len a plus a len x, right? So now we are breaking it down to have two functions, right? And one function is going to apply the product rule, and this is also we are going to apply the product rule. When we are done, then we combine all. So let's begin with the left hand side. So derivative of the left hand side will be equal to 1 y prime over y. So we are done with that, right? And we are going to handle this x len a, right? And this we know that our u is x, our v is len a, right? So our u prime will be 1 and our v prime will be, this is len a. So we take 1 over a times derivative of a is 1. A is a constant, right? When you differentiate a constant, you get 0. So times 0. So this whole thing here becomes 0. Once we have that, that means that the first term is going to be uv will be equal to, our u prime is 1 and our v is len a, plus our v prime is 0 times our u is x, right? So we have the first term to be len a because this will give us 0. So it means that when we differentiated x len a, we had len a, right? So we are going to consider the second term, which is a len x. So we differentiate a len x. Here our u is a and our v is len x. Okay, so u prime will be what? 0 and our v prime will be 1 or less. So u v will be equal to u prime v plus u v prime. So we have 0 times v len x plus a v prime is 1 on x, right? So basically we are going to have a over x for the derivative of the second term. So it means derivative of a len x is a over x, right? So we are done with this, we are done with that. Let's combine the two. So we are going to say that y prime over y is equal to the first term we had this, right? Len a plus the second term we had a over x, right? So it means that the first derivative is len a plus a over x multiplied by y. So we can spread the y, then we have our first derivative to be y ln a plus a over x y. Okay, so this becomes our first derivative. If you want the second derivative, then we are going to use this to find the second derivative. Okay, so since our first derivative is either this or that, then it means we can either use this or this to find our second derivative. So for the second derivative, we have y prime prime equals, let's spread this throughout the bracket, right? So we have y ln a plus ay divided by x. Okay, so this is what we are going to differentiate. We have already dealt with this. Okay, so this we are going to apply the product to, then we apply the quotient rule on this. Okay, so here we are going to have y ln a here, u will be y, and v will be ln a, right? So our u prime will be y prime, and our v prime will be 1 over a times 0, and that is 0. Okay, so it means that our uv will be equal to y prime times v plus u times v prime, which is 0. So our first term is this, right? So this is what we have for differentiating this. Let's come to this. We are going to use the quotient rule, right? So this implies that our u will be ay and our v will be x. So u prime will be, we are going to use the product rule on this. We differentiate a, which is a constant, we get 0, maintain y, right? So 0 times y will become 0 plus, we maintain y, differentiate y. So we're going to have a y prime. So it means that our u prime will be a y prime. Then we differentiate v to have v prime. So that will be 1. So we have v prime to be equal to 1, right? So u over v will be equal to u prime v minus u v prime divided by v squared. So we're going to have u prime is ay prime, and our v is x, minus our u is ay, and our v prime is 1, divided by x squared. So we have ax y prime minus ay divided by x squared. So this is the derivative of the second term. Okay, so we have this for this. So we're going to combine this and this to have our second derivative. Okay. So when we do that, then we're going to have y prime prime equals y prime ln a plus ax y prime minus ay divided by x squared, right? And we know that this is from the first derivative. Y prime is the derivative. So now that we have our second derivative that involves our first derivative and involves our y, we can decide to substitute them inside so that we have the complete solution, right? You can do that by yourself. So that is the derivative. So you either substitute this into it and this into that. Okay, so that is the end of question number 17. Let's move on to question number 18. So with question number 18, we want to find the first derivative of y equals ln into sine 3x, right? So we know that we have y equals ln into sine 3x, right? So this we are going to apply the chain rule. So we're going to have y prime equals, the chain rule says that differentiate the function, right? The function inside, okay? And you know, if you want to differentiate a function inside the length function, you take 1 over the function inside the length function times derivative of the function inside the length function, and that is going to be cos into 3x. Then we differentiate the function inside the length function, right? And that is going to be 3. So we have times 3. So we're going to have 3 cos into 3x divided by sine into 3x, right? So this is our first derivative. But remember that tan into 3x is equal to cos into 3x divided by, no, cos over sine is cot x, right? So we have to be that right here. So it means that our y prime will be equal to 3 cot into 3x. Okay, so we have the first derivative to be 3 cot into 3x. So this becomes our first derivative to this particular problem. Very, very easy. You have to follow the procedure and you arrive at the right answer. Now let's move on to question number 19. So question number 19, we want to find the first derivative given that y equals ln into 3x squared plus 2x minus 1. So we're going to have y prime to be equal to, you know, derivative of a function inside the ln. You're going to take 1 over the function inside the ln function times derivative of the function inside the length function. I know that derivative of 3x squared is giving us 6x plus derivative of 2x is 2. Derivative of negative 1 is 0, right? So we have our first derivative to be 6x plus 2 divided by 3x squared plus 2x minus 1. So this becomes our first derivative to this particular problem. Very easy, right? So this is about mastering the problems. Once you master the process, every question becomes easy for you. Now let's move on to question number 20. Question number 20, we want to find the first derivative of y equals e to the cos x, right? So we know that if you want to differentiate a function on the exponential function, you first keep the function times derivative of the function on the exponential function, and that is going to be negative sine x, right? Derivative of cos x is negative sine x. So we have y prime to be negative sine x e to the cos x. Very simple. Very, very simple. So let's move on to question number 20. So with question number 21, we want to evaluate dy dx if x squared y plus 6y plus x is equal to 0 using the implicit differentiation. Okay, so this we have here using the implicit differentiation, x squared y plus 6y plus x equals 0. Implicit differentiation means that you have many functions, right? And you are going to differentiate all at a time. Okay, so you differentiate this to x, you know, we are using the product rule. So you differentiate to x, then you maintain y plus maintain x squared, then you differentiate y, and that is the y dx plus 6, it differentiates 6, and that becomes 0. 0 times y is 0. So you have 0 plus, maintain 6, then differentiate y, that becomes dy dx, plus differentiate x, and that becomes 1. So equals 0, right? Now we need dy dx. So let's group those with dy dx at one side. So x squared dy dx plus 6 dy dx plus 1 plus 2xy equals 0. So this dy dx is common. So we factor that out into x squared plus 6 plus 1 plus 2xy equals 0. We need this. So we send this to the other side. Then we're going to have dy dx into x squared plus 6 equals negative 1 negative 2xy, right? So we divide here by x squared plus 6, here by x squared plus 6. So this cancels this, and we have dy dx equals negative 1 minus 2xy divided by x squared plus 6, right? So we have this as our dy dx. Therefore, using the implicit differentiation to find dy dx, given that x squared y plus 6y plus x equals 0 is this. Very easy, right? You know, the only way that this thing will be very easy for you is to master the product and the quotient rule. So watch and watch over and over, and everything is going to be perfect. Let's move on to question number 22. Okay, so with question number 22, we want to find the first derivative to this particular function. Okay, and this function is of two terms. This is first term and this is second term. In this term, we have to apply the product rule, right? So let's say that e to the x sine into ln 2x, right? This, we are going to handle this first. So our u is equal to e to the x, and our v is sine into ln 2x, right? So our u prime will be equal to e to the x. You know, when you differentiate an exponential function, it remains the same, which is the u. So we have u prime, and v prime will be equal to, when you differentiate this, we are going to have cos into ln 2x times derivative of ln 2x is 1 over 2x times 2, right? So our v prime will be equal to cos into ln 2x divided by x, because this will cancel this, right? So we have our v prime, we have u prime, u, and v. So u v will be equal to u prime v plus v prime u. So we're going to have u prime e to the x, and v is sine into ln into 2x, plus our u is e to the x times our v prime is cos into ln into 2x divided by x. So this is the derivative of the first part, right? So the derivative of e to the x sine into ln into 2x is equal to e to the x sine into ln into 2x plus e to the x cos into ln into 2x divided by x. So that is the derivative of this. Now let's come to the second part. derivative of e to the cos x, right? And that is going to be negative sine x e to the cos x, right? So now we have first part, we have second part. Let's combine all. So we're going to have our first derivative to be equal to this e to the x sine into ln into 2x plus e to the x cos into ln into 2x, right? Divided by x minus the second part, which is e to the cos x sine x. So this becomes the derivative to this particular function. Therefore, we have, let me write it nicely, sine into ln into 2x plus e to the x divided by x cos into ln into 2x minus e to the x, e to the cos x sine x. So we have that done. So that is the derivative of this particular function. And that is question number 22. Now let me solve one more question and call it a day. Okay. With question number 23, we want to find the slope of the curve. This is the curve at x equals 1. Okay. So when you have a question of this nature, first differentiate the curve, right? To have your first derivative, right? Then you substitute the value of x inside, and then the result you obtain becomes your slope or the gradient. Okay, so y equals 9x squared plus 7x4. Derivative of that is going to be, this will be 18x plus 28x to the 3, right? And we have x at 1. Okay, so we're going to substitute x equals 1 into this. Then we find the gradient. Okay, so this is basically the gradient. So m equals dy over the x, which is equal to 18 into 1 plus 28 into 1 cube, right? So our gradient will be 18 plus 28, and that is equal to 46, right? So we say that the slope or the gradient is 46, right? Okay, so we have that. Now, in question 27, in question 24, we have to find the equation of the normal to the curve, this same curve at the point 1 and 2. Now, what we need to be able to satisfy this particular question is the gradient. And it's not just going to be the gradient, but it's going to be the negative reciprocal of the gradient, because we are talking about the normal. Normal means it's making an angle of 90 degrees. Okay? And when it makes an angle of 90 degrees, it means that it is perpendicular. So if you need the gradient, it's going to be 1 over the gradient that you obtained, right? So here, our gradient will be equal to negative reciprocal of the gradient that we have here, since it's normal. And that becomes our gradient. And we know that at 1, 2 means x1 is 1 and y1 is 2, right? So Once we know these informations, then the rest is substitution. Right? So we substitute them inside. Then we have y minus y1, which is 2, equals negative 1 over 46 into x minus 1. Right? So we multiply here by 46, this by this, 92 equals negative 1 into x minus 1. So we have 46 y minus 92 is equal to negative x plus 1. Okay, so when we equate, we group the terms very well. We are going to have 46y, this comes here, plus x, this comes here, minus 92 minus 1 equals 0. So we have 46y plus x minus 93 equals 0. So we can say that our equation of the normal to the curve this is 46y plus x equals 93. So beautiful, right? So that is the result to question number 24. Let's move on to question number. Okay, so this being our last question, we have done a lot, right? So this is going to be our last question, which is question number 25. Okay, so with this question, we have this function right here, and we want to find the first derivative of the function, right? So first of all, our f of x equals a cos x plus b sine x plus k divided by sine x, right? So we know that whenever we have two functions that are dividing each other, then it means we are going to use the quotient rule, right? So in here, we have this dividing this. So it means you are going to apply the quotient rule, which says that two functions dividing each other, first differentiate the first function, maintain the second function, minus keep the first function, differentiate the second function, divided by square of the second function. Right, so let's identify our u and our v. So our u here will be equal to a cos x plus b sine x plus k. And our v will be equal to sine x, right? So once we have been able to identify our u and our v, then we can go ahead and find our u prime and our v prime. So our u prime will be equal to derivative of a cos x. A is a constant, so when you differentiate a, is going towards 0. So 0 times cos x becomes 0. So using the product rule, the first term, differentiating the first term on this becomes 0. Then we maintain a, differentiate cos x becomes negative sine x, right? Then we differentiate b, becomes 0. 0 times sine x becomes 0. So plus we maintain b, then we differentiate sine x. Differential of sine x becomes cos x. So we have cos x. Then when you differentiate k, which is a constant, that adds to becomes 0. So that is u prime is this, right? So we have to get our v prime, and that is equal to, this is the v. So v prime becomes derivative of sine x, and that is cos x. Okay, so once we have u, v, u prime, and v prime, then we go ahead and say that u over v is equal to u prime v minus u v prime divided by v squared is going to be, u prime is a negative a sine x plus b cos x multiplied by v, and the v is sine x, minus u, and our u is a cos x plus b sine x plus k, right, times v prime, and the v prime is cos x, so we have times cos x divided by v squared, and the v is sine x, so we have sine x all squared, right? So we're going to say that, we can expand this bracket, right, and we can expand this as well. So let's try to do that. So we're going to have negative a sine, this and this becomes sine squared x, this and this becomes plus b cos x sine x. Then we expand this as well, it becomes negative a cos squared x, negative b sine x cos x, minus cos x k cos x. Okay, so that is what we have, all divided by sine x all squared, right? So from here we can see that we have this and this that has to be, they have something in common, right? And this also has something in common. So we know that this and this will go off, right? Because this is positive b cos x sine x, and this is negative sine x cos x. So this cancels this. And then this and this becomes negative a sine squared x, negative a cos squared x, minus k cos x divided by sine squared x, right? And we know that negative a is common to these two terms, so we can factor that out. So when factor that out, we're going to have sine squared x plus cos squared x minus k cos x divided by sine squared x, right? So we are now going to have minus a into, you know that this is an identity that is well known to be what? Positive 1. Sine squared x plus cos squared x is 1. So we have into 1 minus k cos x divided by sine squared x over here. So in all, we are going to have minus a minus k cos x divided by sine squared x. Okay, so this is what we have right now. Okay, we are not done yet. We can still simplify this to have a simple expression, right? So remember that this is the same as minus a over sine squared x minus k cos x over sine squared x, right? And we know that 1 over sine squared x is equal to cosec squared x, right? So this here this will go and replace this. And also remember that cos x over sine x is equal to cot x, right? And 1 over sine x is equal to cosec x. Okay, so we are going to do that substitution. So we come up here, then we say that negative a divided by sine squared x minus k cos x divided by sine squared x, right? And this is the same as minus a times 1 over sine squared x minus k times cos x over sine x times 1 over sine x, right? And we know that the whole of this is cosec squared x. So we have minus a cosec squared x, right? Minus k times cos over sine is cot x, right? So we have cot x times 1 over sine x is cosec x. So we have cosec x. Okay, so we're going to have minus a cosec squared x minus cosec x cot x. Okay, right? So let me write it very, very nice here. So here, the derivative of this function is minus a cosec squared x minus k cosec x cot x. Okay, so that is the first derivative to this particular problem. So interesting, right? Now we have been able to solve the 25 problems that we targeted to do. Hands of applause for all of us. And thank you too for watching up to the end. Bye-bye.